It is another exciting day in Algebra 2 here. We are going to be looking at our 9 parent functions today. All of Algebra 2 is going to be focusing on these different functions throughout the year. We will take time to look at each one more in depth. These first 3 we've already explored more conceptually than anything, but what we're looking at today is the equations, the graphs, and the names, and getting comfortable associating all 3 of those together. So starting with linear, that is when f of x is equal to x, and your graph, apologies, I had a knock at my door, so that graph looks like a diagonal line going through your x-axis, sorry, your origin. Quadratic, that equation is x squared, and that, of course, looks like our standard parabola that we're used to seeing. Exponential, this is a to the x power, where a is any number other than 0 or 1. Sorry, these graphs aren't as pretty as I would have liked them to be. Okay, absolute value, your goalpost absolute value of x, and that graph looks like a big V. Square root of x, that one starts at the origin and kind of curves up, sort of like a parabola shape, but only half of it. And then logarithmic, which we say log of x. This one is mildly related to exponential, and we'll get into that more when we look at the characteristics, but it's going to look like this, and instead of having a horizontal asymptote, it has a vertical asymptote. Rational, 1 over x, so because x is in the denominator, x cannot be 0, so you're going to have a horizontal asymptote. And also, there are no inputs for x I could put here to get an output of 0. So you will also have a vertical asymptote at y. And the way this graph looks is, if you recall your quadrants, 1, 2, 3, 4, you have a curve in quadrant 1 and a curve in quadrant 3. Okay, cube, this is x to the 3rd power. This one looks kind of like a parabola where the second arm got lazy and flipped upside down. And then your cubic, this is the cube root. This one is similar in shape to the cube, but it's kind of tilted on its side. All right, so those are our 9 parent functions. And what you have on the next page is those equations along with the graphs. And so this is what we're going to be looking at as we list the different characteristics for each. So starting with linear, domain, my x values. Here I have all real numbers. Same for my range. It passes through the origin, so that means my x and y intercepts are both 0, 0. It does not have a maximum or a minimum. And as I go from left to right, I am walking uphill the entire time. So it is increasing everywhere, and it's never decreasing. It's positive starting at 0 and off to positive infinity. And I do not include the 0 because when x is 0, my y value is 0, and the number 0 is neither positive or negative. So we don't include the 0. Similar, so negative, that is from negative infinity to 0. Again, I'm not going to include the 0 because 0 is neither positive or negative. Looking at quadratic, my domain is also all real numbers. This time my range is all y values greater than or equal to 0. We also pass through the origin, so we've got that x and y intercept both at 0, 0. This parabola does have a minimum, and that minimum is at 0, 0. And if you were asking about the minimum value, that would just be the y-coordinate. We're increasing, starting at that vertex, going off to positive infinity, so 0 to infinity. And then similarly, when we were looking at where we switch from positive to negative, we don't include the 0 because 0 is neither positive or negative. It's similar here when you are switching from increasing to decreasing or vice versa. That point where you're changing direction is neither increasing or decreasing. So we're going to use parentheses there as well. We're not going to include that point of change. So it's increasing on the right and decreasing on the left from negative infinity to 0. Again, I'm not going to include the 0. And this is positive everywhere except at 0. So I'm going to do those 2 intervals to reflect that at 0 we are excluding that, and it's never negative. On to exponential. My domain is all real numbers. My range is that y is greater than 0, but it's not equal to 0. I do not have an x-intercept because we don't cross the x-axis, but I do have a y-intercept, and how can I figure out what that y-intercept is? Well, our y-intercept is when x is 0. If I plug in 0 here for x, that's 2 to the 0 power, which is 1. And that will be true regardless of what your base is. Any number to the 0 power is going to be 1. So if this was 3 to the 0, 4 to the 0, 5 to the 0, it doesn't matter. Your y-intercept will still be at 0, 1. This one does not have a maximum or a minimum. We are also walking uphill the entire time from negative infinity to positive infinity. It does not ever switch to decreasing. And it is also positive everywhere. It never crosses the x-axis and it never becomes negative. Okay, moving on to absolute value. There is our graph. We can see that the domain is all real numbers. And our range is that y is greater than or equal to 0. We pass through the origin. So we have that x and y intercept at 0, 0. And absolute value functions also have a vertex similar to parabolas. So this one does have a minimum at 0, 0. Your minimum value would be that y coordinate. We're increasing from 0 to positive infinity, and we spoke earlier about why we're using parentheses there. Decreasing from negative infinity to 0. And this one's also positive everywhere except at 0, because 0 is neither positive or negative, and this never switches down to negative. Moving on to square root, this one starts at 0, 0 and goes on, so my domain is that x is greater than or equal to 0. Same for my range, y is going to be greater than or equal to 0. We're at the origin for our x and y intercepts. And then this one does have a minimum value because it stops at 0, 0. It does not go any further than that. So there's your minimum. We're increasing from 0 to infinity because that's where I have x values. It never switches to decreasing. It's also positive on that entire interval from 0 to positive infinity, and it never becomes negative. All right, now looking at logarithmic. So let's start with just our domain and range. So we've got this vertical asymptote here now, so x never crosses that, which means our x values have to be greater than 0. But y is going to continue up and down forever, so our range is all real numbers. So if you look at the difference between logarithmic and exponential, do you see that the domain and range have switched? That's because exponentials and logs are what we call inverses of each other, which we'll get into the definition of more here in a few weeks. But that means that your x and y's are flip-flopped. So where I used to not have an x-intercept, now I will not have a y-intercept. And where I had a y-intercept at 0, 1, I'm going to have an x-intercept at 1, 0. This one also does not have a maximum or a minimum. And you're walking uphill the entire time, but this is just over my domain when x is greater than 0. It never switches to decreasing. And then it's positive starting at that x-intercept, so when x is greater than 1, and it's negative when x is less than 1. Again, we don't include the 1 for either of those portions because 0, which is the y value there, is neither positive or negative. Okay, rational. For both the domain and range, we have all values except 0, so x does not equal 0 and y does not equal 0. For that reason, we are not going to have an x or a y-intercept. We also do not have a maximum or a minimum. And if I look at both portions of my graph, the one in the third quadrant and in the first quadrant, those are both walking downhill. So it is never increasing, but it's going to be decreasing over both of those intervals, from negative infinity to 0, and then again from 0 to positive infinity. It's positive over here in this first quadrant when our x values are greater than 0, and it's negative down here in our third quadrant when the x values are less than 0. Moving on to cube, my domain is all real numbers, along with my range. Handy dandy origin for our x and y intercepts. We don't have a maximum or a minimum. And then as I'm going from left to right, I'm walking uphill. I have a point of inflection, but then I continue walking uphill. So this is actually increasing everywhere, and it's never decreasing. It becomes positive here at that origin, so when x is greater than 0, and it's negative everywhere else when x is less than 0. Again, we don't include the 0 because 0 is neither positive or negative. And then looking at cubic, sorry, paper's not cooperating. Okay, cubic, my domain and range, again, are all real numbers. Passing through the origin gives me my x and y intercepts. I don't have a maximum or a minimum. And I'm walking uphill across the whole thing, even across that point of inflection. It never becomes decreasing. We're positive starting at that 0 when x is greater than 0, and we're negative when x is less than 0. So looking at these two functions, they have all of these same characteristics, but their graphs look vastly different. So one suggestion I'm going to make to you is if you're ever in a predicament where you can't remember which one looks like which, my suggestion is going to be to make a table of values and sketch a little graph so that you can get an idea of what you're working with. So if I'm starting with x cubed and I make a little xy table, well, when x is 0, 0 cubed is 0. When x is 1, 1 to the third is 1. When x is 2, 2 to the third is 8. So that kind of gives me an idea for a few of these points. And then I know I've got this part so far, but if I want to see what's going on the left side, I need some negative numbers. So like negative 1. Well, negative 1 to the third power, that's negative 1 times negative 1 times negative 1. The negative times the negative gives me a positive, but then that third negative switches it back to a negative. So when you have odd powers and you're using a negative input, your output will remain negative. So I've got negative 1, and then I can throw negative 2 in there as well. Negative 2 to the third power will give me negative 8. And then I can connect the dots, and there is my cube function, cube. For cubic, cube root. Again, I need to make a table, but I need to be kind of careful about the inputs I put for x, because if I don't put in perfect cubes, my outputs are not going to be whole numbers. So I can, again, start with 0. The cube root of 0 is 0. I can go with 1. The cube root of 1 is 1. But after that, I need a perfect cube. Well, 2 is not 1, 3, 4, 5, 6, 7, but 8 is a perfect cube. The cube root of 8 is 2. So I do have, right now, 3 points on my graph. So I know what's going on the right-hand side. To figure out the left-hand side, I need some negative values. So I can go with negative 1. The cube root of negative 1 is negative 1. Beyond that, negative 8. The cube root of that is negative 2. And now I've got an idea of what I'm looking at. So if you are ever forgetful of what your graph looks like, my suggestion, make a table of values and sketch it together. So your key takeaways from today and going forward with these parent functions are that if I were to give you one of the three, those three being the graph, the name, or the equation, you could match the other two. So that is your task right now. You don't need to necessarily memorize all of these properties, because if you can visualize the graph, you should be able to answer those questions. But name, equation, and graph you need for all 9 of these. And that wraps up our notes today on parent functions.